In this module, we will see some basic properties of open and closed sets. I immediately begin with a proposition. Any union of open sets is open. Any finite intersection of open sets is open. Now the first part I have already hinted how to prove. It's quite easy, but let's, for the sake of completeness, give a full proof. Let u lambda be a collection of open sets. Okay, let X be an element of union of u lambda. Okay, so I'm considering a collection u lambda of sets. It's indexed by lambda. It could be countable, uncountable, I don't really care. So let me just be precise, write lambda coming from some indexing set I. Okay, lambda coming from I. So let X be an element of u lambda union. Then X belongs to some u lambda 1. X is an element of some u lambda 1, right? Because it's there in the union. But X is then an interior point. Of u lambda 1. This means BXR is subset of u lambda 1 for some r greater than 0. Hence, BXR is subset of union of u lambda as lambda runs through I. Hence X is an interior point of the union. Okay, now suppose u1 to uk are open. We are on to the second part now. We want to show that intersection of this ui I equals 1 to k is also an open set. Now here is the catch. First part, if the intersection is empty, then nothing to prove. So somewhat counterintuitively, the empty set is an open set. Why is that the case? The reason is because the definition of an open set is that every point in that set is an interior point. But the empty set has no points. Therefore, this is vacuously true. Okay. So the empty set is an open set. So if the intersection is empty, nothing to prove. Part 2, if X is there in the intersection of ui, then for each I we can find Ri greater than 0 such that Bxri is contained in ui, right? The only way by which X could be in each of the ui's is if X is an interior point of each one of the ui's, simply because each ui is open. Because each ui is open, corresponding to this ui, I can find an Ri such that Bxri is contained in ui. This is the definition of an interior point and open set. Okay, choose, as you can guess, R equal to minimum of R1 to Rk. okay, choose the minimum, then Bxr is contained in Ui for all I, because it is the smallest of the Ri's, okay. Hence Bxr is contained in the intersection of the Ui's as required. We have shown that there is some R such that Bxr is contained in the intersection, therefore X is an interior point and therefore the intersection is an open set. Okay, so the next question is, what about similar things for closed set? Is the union of a closed set closed? Is the infinite intersection of a closed sets closed? But before that, let's tie up the relationship between closed sets and open sets neatly in the next proposition. The next proposition. A set U is open if and only if R minus U is closed. So I remarked earlier that closed set is sort of the dual of an open set and vice versa. That is captured precisely by this proposition, which says a set U is open if and only if its complement is closed. Okay, how do you prove this proposition? Proof. Let U be open. Let U be open. Okay, suppose X is a limit point of R minus U. Okay, suppose X is a limit point of R minus U. We will show that X cannot be an element of U. X cannot be an element of U. Why is that the case? Well, if X is in U, then Bxr is subset of U for some R greater than 0. Why? Because U is an open set, every element of U must be an interior point, right? But this contradicts the fact that Bxr intersect R minus U is non-empty, right? Because X is an adherent point, it's in fact a limit point, Bxr intersect R minus U must be non-empty for all choices of R, but we have found an R for which Bxr is contained in U. Okay, so this means X is an element of R set minus U, no choice. So what we have shown is R set minus U contains all its limit points, and we are done. Hey, hold on. Didn't we say that a set is closed if it contains all its adherent points, not just all its limit points? Well, not a problem. We just showed that an adherent point is either an isolated point or a limit point. And isolated points have to be in the set itself. Okay? So in fact, to show that a set is closed, you needn't show that all adherent points are there in the set. You can just show all limit points. That is enough, because the non-limit adherent points will automatically be in the set just by the way things have been set up. Okay. So this was fairly straightforward. Now we need to prove the other side. Suppose R set minus U is a closed set. Then we must show U is open. Suppose X is in U, then X is not a limit point. X is not a limit point. X is not a limit point of R minus U, simply because R minus U is closed and therefore it must contain all its limit points. Therefore, for some R greater than 0, BXR must be fully contained in U. Right? This is the only way by which X can fail to be a limit point of R minus U. Hence, X is an interior point of U. Interior point of U. And we are done. Okay. So what we have done is we have shown that a set is open if and only if its complement is closed. So they are both dual notions. Now I can immediately write down this proposition. A finite union of closed sets is closed. Okay. Any intersection of closed sets is closed. Proof follows immediately from De Morgan's laws combined with the previous two propositions. I'm not even going to elaborate the proof. I'm going to leave it to you to figure this out. Okay. So from the facts about open set, we have immediately got the facts about closed sets. Okay. Now I'm going to introduce just two more concepts which are sort of producing closed sets and open set from a given set. Definition. Let A subset of R be a set. We define A closure. This is A written with a bar on top. This is called closure of A. This is nothing but X in R such that X is adherent to A. Okay. And the second is interior of A. This is denoted int A, or sometimes like this. I don't like the second notation because some textbooks use that for complement. I prefer writing interior of A. X in A such that X is an interior point. Okay. So these are two things. I want to define one more thing. I want to give it as a separate definition. Let A subset of R be a set. We define boundary of A. This is called boundary of A. So we want to say that something is a boundary point. Well, this is defined to be the set of all x in R such that x is adherent to both A and R minus A. Something is in the boundary of a set if it sticks to both the set and the outside of that set. So this is a very, very natural definition. Okay, now in a proper course on topology, you explore several relationships between all the definitions that we have given. You will explore some of these in the exercise. But for the time being, this is all I require from basic topology to continue with real analysis. Any other topological concepts that I need will be introduced as and when needed. So we can now proceed to the definition of continuity, after which we shall study the relationship between topological properties and continuity, how they interact. At that time, I will introduce some more topological notions. This is a course on real analysis, and you have just watched the module on basic properties of open and closed sets.